I'll be honest, I saw my friend Oliver, who was in my physics classes. He's going to be in my physics classes next year. Good friend of mine. He recently posted his video on the double pendulum. And I thought, you know what? I love simulations. I want to simulate something. I know Lagrangians now. I know Lagrangian mechanics. So let's do something fun. So I came up with this sort of um, this oscillatory pendulum that sort of swings around like this, but also can, oscillate back and forth. So the setup is that it's a pendulum whose chord is just a spring. So it has sort of two oscillatory degrees of freedom. One is sort of this back and forth pendulum movement, and the other would be this spring bobbing movement. And well, to be honest, I saw this in one of Steve Moll's videos way back in past. But I thought, you know what, let's do this. And I haven't played around with it so much, and I'm gonna do it as I record it. If you want, you can discuss the way I solved it. I think it's kind of nice. If you're unfamiliar with Lagrangian mechanics, it would be a nightmare to solve this. You would be thinking, oh, what's the equation of motion? What are the forces acting on it? We don't do this. We've grown up, and now we only use primarily Lagrangians, which is this really elegant sort of technique, I would say. It's got a beautiful history to it, but I'll leave it to you for now. The idea is that you write some kinetic energy of your system, you write some potential energy of the system, and you find this Lagrangian, which is kinetic minus the potential energy. And then, you want to minimize an action, which is sort of this integral of the Lagrangian over some path, which is equivalent to solving the Euler-Lagrange equation, because it's an Euler-Lagrange type integral. You find with some geometry and some trigonometry this kinetic part, which you notice that you have two perpendicular components of the velocity. So you have this being the velocity. This is half mv squared. The potential, well, you have elastic and gravitational potential energies. Elastic is just half kx squared. Gravitational is mgh, and finding this h takes a bit of geometry, but it's not too bad. One thing to note is that we are using the small angle approximation. So the simulation is not exact, actually. I can make it exact because, approximate, numerically approximate. But even this approximation has an approximation of its own, which is the small angle approximation, right? And it's just because I don't want to deal with the cosine. It's easier to deal with the constant and the quadratic term. And once you solve this, you get your potential energy. Then it almost by magic, you just take a few partial derivatives and a full derivative, and you get sort of this. Let's see, this term here is your generalized momentum. And what the Euler-Lagrange equation says is that the time derivative of the generalized momentum is sort of a generalized force, or yeah. And it confused me for a long while how you can differentiate with respect to q dot and not change q. And well, there's a nice resource on this. To be honest, I don't understand the entirety of it, and it turns out that the reason is hidden deep within differential geometry, which is a sort of nice perspective to look at Lagrangians and Hamiltonians, the fiber bundles and tangent bundles and tangent spaces and whatever. I don't even understand that. I'm probably going to take a class on that in the future, learn about it, or read a book on it. But on this post, I discovered this book, Applied Differential Geometry by William L. Burke. In the Yes, the opening page of the book, um, he says, to all those who, like me, have wondered how in the hell you can change Q dot without changing Q. I think this is really amusing. But yeah. So you take these partials and you get your equations of motion, and some of these terms might seem familiar to you. For example, mx double dot. X double dot is just acceleration, so this is saying ma equals to something, and that's something you would know from Newton's laws, is a force. Now, this is sort of a generalized force, so you may know that this is force, but you may know that this is minus kx, ma equals minus kx, that's just your Hooke's law. Mg, well, this is just free-falling object in gravity, but then you have sort of these gravity and your angle and your length and your angle all coupling here. So because you have these two oscillatory systems which are oscillating and sort of in these sort of two directions, you have not only sort of the spring motion and the pendulum motion, but you also have sort of these coupling terms here. For example, this term though, and this term, these are sort of coupling terms. And on its own, the system here, it's in two variables, x and theta, is coupled because you have one equation here which has theta here, but you have another equation here which also has it. So you can't really solve these nicely, except maybe with computation. And I wrote some notes on, sort of, again, this should look somewhat familiar to you. Sort of, this is mr squared, alpha. Mr squared is kind of your moment of inertia. You remember moment of inertia of like pendulum. It's just dm r squared. So the dm integrated for like a Dirac delta, just so it's too advanced maybe. But yeah, this is sort of your torque, and lo and behold, this is a form of torque. But again, you solve for x double dot, theta double dot, and get these, and let's see. Now, you want to solve these numerically, and so what you do is you can do this with Euler's method, just kind of naive, but I like RK4, sort of this differential equation numerical solving technique. It's not super easy to understand, but it's also not super complicated. In essence, I can probably draw this. In essence, what you're doing is, say you have a point here, and you know that it has a slope. So this is the slope, right? So a naive way to find the next point on your curve is to just multiply this slope by dt and get this next point. But what you would notice that maybe the slope here is this, right? And what you would notice is that certainly if this is sort of a smooth curve, the slope would, in that sense, be going from here to here. And so the average slope in the entire journey is more like the average of the slopes here and here, right? That's the general idea. And in essence, RK4 sort of, instead of going full way through, it takes sort of a half step, right? So it goes halfway through and sees what is the slope here. So in our example, maybe it goes halfway through, it comes here, and now it says, oh, maybe the slope is this, so maybe you should update that. So it takes sort of these incremental updates to the information you're encompassing within your calculation for the next step, and doesn't just take the naive step, it just includes, so it takes your half step, and it takes another half step, and then it takes a full step, and so on and so forth, and then it takes the average in some particular way. You can do all the math, and you don't need to prove this. You can, but can do all that we want. So essentially, you take your function f, which transforms your vector y. Now y is where's y? It's x theta x dot theta dot. So essentially your variables, you linearize them in a vector, and you want to solve the differential equation y dash equals f of t comma y. Y dash will be x dot theta dot x double dot theta double dot, which is just the time derivative of each of the each of the components of y. You can, if you want to learn about numerical computation, I suggest you take the time, because it's too short of an introduction to numerical methods. But essentially, you have some way to solve ODEs numerically with given initial conditions, derivative function, and some parameters, and some time step dt that you want to take. The smaller the dt, the more sort of accurate your solution would be, in a sense. Then you define your derivative function, again, using whatever we calculated here. Right, so you had x double dot, theta double dot, and you already have in y x dot and theta dot. So these two are all you need to calculate, and then you just return your derivative vector, and then you run the main loop where you just, iteratively calculate, you had y0 with the RK4 step, you can calculate y1, and then you do the same for y1 and calculate y2, and so on until you reach yn for like the specified time span, right? It's not really what's the most important thing. I just want to show something cool, but I don't want to, just jump into it. And then you have, once you've solved the ODE, then it's just the visualization. You work out the geometry. So whatever your generalized coordinates were, for us it was x calculated from the natural length L of the spring, and the angle theta from the vertical. You translate that to your coordinate, compute the positions for all the solutions on your curve, and then you can create your scene or plot. I like scenes better because it's no background, and I just like no background. And then you update the camera, and you sort of, I don't want to get into the specifics of why I want to update this camera, and I could have also just moved all the points and so on, but I just don't want to do it. You generate a trail, that's what I want to do. So I want to not only look at the pendulum itself, but sort of where the bob sort of went through. 500 is maybe a little bit too much. 50 should be fine, but okay. In my opinion, 100 is good. The way I do it is, it's just, this is some complicated function which has an easing to it. So you can think of it as the trail being high in alpha, close to the bob, but sort of fading out away from the bob, and this is just an easing function for that. I created it. Actually, I didn't create it. You can find this like online. And then you start with the trail. Oh, I also do this thing called lifting and observable. You can, again, observables are another nice thing. in GLMarquee or integrated with GLMarquee. It's standalone package, however, where you just, you don't need to keep updating things yourself. And once you update it, it automatically reflects in your animation. You don't have to like delete the thing that was previously there and then update it with like a new rendering object. It just does it automatically. I also do a chord color shift. So, sort of simulate the tension in the chord, um, which I think was nice. It's looking better than just a black chord. Um, and yeah, then I just run the frames. Um, so let's start. Um, my initial conditions for now are just simple pendulum, and I've um, commented out the trail because it just gets in the oops. Oh, ah, for some reason I just deleted it, or just escaped the entire thing. I need to rerun it. And the thing with Julia, if you use Julia, is its first runtime. And again, I was just using Z for the first time, to be honest. And I can't figure out how to, set up the Julia language server, because for some reason, this is supposed to be the language server, if I'm not mistaken. And it only shows me this one thing. Whereas, for this, oh yeah, I can, what was it? There was some kind of kernel settings here. You know what? Never mind. Forget about it. Anyways, I cannot figure out how to do this. So I'll just do it the old school way. Right. Um, and I guess that means that we have to wait for GLMarquee to load, which can take anywhere from 12 seconds on my laptop to even 2 minutes sometimes. Oh, wait, that was super fast. Um, what's this? Get it. Let's see. What packages do I have? I have in this particular shared environment. I love shared environment in Julia. Um, man, super slow for some reason right now. Um, no longer slow, but um, and let's run this for the first time. Should be a nice first timer. And let's see how it goes. There we go. We have the marquee scene loading up. Perfect. Set it up prop. There we go. Perfect. It seems like a spring bobbing up and down. Right. Now, actually, I'm unsure of whether the next one will be a simple pendulum swing or will be a combination already. I'm unsure. I haven't even checked this. But let's see what happens. Okay, this is so you can see how the tension in the spring is changing, but it's more or less doing this sort of swing motion. In Steve Mold's video, I saw actually the spring changing its motion and switching back and forth between the springy motion and the pendulum oscillatory motion. Um, but fine, let's now do this one. Um, yeah, would you look at that? That's so insane. I think that's super cool. Let me redo the clear And how many trails? Fine. 100 trails. That should do fine. Yeah, this is fun. Let's try some ooh. How about some random thing? I have to now make sure that, because of the if you look at the denominator here, the denominator has an L minus X, so I want X to be greater than L, but I think rand only gives a number from 0 to 1, so it's should be fine. Random, sure. This can be problematic a little bit. You know what? Let's not do this because of the singularity. This should be fine. We can also just do this times 2 pi, but or times pi. Yeah, yeah, but it doesn't matter. It's not too critical. Um, yeah, for a moment there, I thought that it was. Oh, you see the Steve Mole thing. You see the Steve Mole thing. It's oscillating between sort of these two. It's oscillating between these two um, modes of movement. You can see that right now it's just bobbing like a spring, but then it sort of shifts into being a pendulum. See, so it's pendulum, and then it then again bobs like a string. I think this is super cool. So just some scribbles on the board and some numerical computation, and you can take a look at this interesting phenomena. Again, this is seems like, oh, this one's more stable, more predictable. I think this is a chaotic system. I'm not sure, but I think this should be a chaotic system. Let's actually let's see what happens if we, you know, give it a huge kick. Let's see. I just want to see what happens. How chaotic is it? Um, let's say, I don't know, 10. This may be breaking the simulation, but we'll see what happens. All right. Because it's a because it is a stretchable thing, it doesn't need to like just go all the way up there. It can also just oscillate here. I think what would be interesting is if you have the angle also be um, sort of beyond pi by 2. So um, maybe like 2 by 3 times pi, right? That seems fine, and maybe we can lower this down a bit then and make it negative so that it's swinging sort of down this way. Let's see how this goes. Yeah, that seems interesting. It's almost like it's defying gravity, but it's not, because when it's doing that, it's releasing all that elastic potential energy. Let's do that maybe for a longer duration. Where's my duration? Supposed to be somewhere in here. Oh yeah. So let's do it for like 30 seconds. And look at how quick Julia is, by the way. Shout out to Julia. Hate the first runtime, but well, after that, it's a blessing. Yeah, just take a look at that. I think it's just amazing. Oh, ignore the background music playing. Um, but yeah, I think this is amazing. And yeah, stay curious. May the kid remain. Yeah, and I'll see you sometime later.